name is Electrical Vehicle Cool Motion. I'm Shaymat Maghfour and my partner is Kylie, and we made a GUI module for control and optimization of temperature regulation in EV battery thermal management systems, which is also referred as BTMS. So this document is pretty long, but it's worthwhile at least skimming through. So Kylie and I are both mechanical engineers, and we find this topic fascinating because the demand of electrical vehicles will increase. And of course, with any product, there is room for improvement, for optimization. And one of the main challenges for electrical vehicles is to keep the temperature of the battery and the coolant and all of the components within a certain range. And this is like the most challenging part for the electrical vehicle industry. For example, during winter temperatures, this reduces the battery efficiency and capacity, while high temperatures, like in the summer, accelerate chemical degradation and lead to extreme safety risks such as fire or explosions. And so that is our motivation of why we wanted to create this, to show the importance of, keeping temperatures of components within a certain range for safety reasons, but also to have more efficient vehicles later on. And so we created this GUI module, which is called an Electrical Vehicle BTMS Analysis Tool. And it enables users to explore how varying the drive load, coolant type, and ambient temperatures affect the coolant and battery temperatures during operation. And this was our initial prototype schematic that we were envisioning to create the GUI. So you can see here that we have the overview, the diagram, and results tab. So there's 3 different tabs. And this prototype, of course, was initially drafted on PowerPoint. So here's the governing equations. Again, I won't go into much detail, but this is here for your convenience if you want to learn more about how we created our model. And then we have, of course, all of our tables for the thermal properties, for coolant, for the air and water, and also the battery. And then Kai will show a demo at the end of this video, which will show how the GUI is used and all the different tabs that we have. And then please look at the check your understanding questions, because as you're playing around with the GUI module, it's good to go through some critical thinking. And then, of course, there are limitations and future improvements, and ending with the annotated bibliography.
Hi everyone, my name is Kai and I'll be going through our calculation code behind our model. Our Python file for the calculation is called thermo _prop, which stands for thermal properties. And in this file, the user inputs the drive load, the coolant type, and the ambient temperature. And this file is able to calculate the max temperature, the average temperature, and the coolant temperature, and the pump power as well. And yeah, we'll dive into our calculation file, starting with our imports. First, we import our basic libraries like NumPy and Pandas for data frames. Then we also import our SciPy libraries for integrating our ordinary differential equations, which we'll start calling ODEs. All right, then moving on to our first function, we have 3 different coolants that are used as our inputs, and they are EG50 ethylene glycol, which is commonly used as car coolants because it has a great cooling capacity, and it's also relatively low. It requires low pump power requirements, and yeah, but it is toxic to the environment, however, so that is a downside. And then there's PG50, which is propylene glycol, which is less toxic, but it is worse in both cooling and power requirements. Novec 7000 is a specially engineered fluid by 3M that has a low power cost, but it has to be run in 2-phase. We included that as well. Then moving on to the next section, this part of the code is not used directly in the solver, but they are useful for documentation and sanity checking our numbers after getting our numbers. And it is also a reference point for boiling point, freezing point, viscosity, and so on and so forth. So this is pretty useful information to have on hand. Next, we move on to section 3, battery module parameters. This is where we define a dictionary of battery module properties. These represent a simplified 6-cell EV battery modules under a lumped capacitance assumption. So they're assumed to be 1. For example, M cell and CP cell define the thermal mass, and IJ sets the thermal conductance between the cells, and the Q cell relates the electrical power to heat generation. And these parameters form like the foundation and the parameters behind the battery modules. Moving on to the next section, the drive load equation. Here we define the battery module model class to compute the heat generation from the electrical load. And the key idea here is that electrical power isn't fully efficient and some energy is lost to heat. So the model calculates the power per cell and the heat generated per each cell and the total module heat as well. And this is based on different drive loads as inputs. We have 250 watts, 300 watts, and 400 watts to see how much heat the battery produces and the different wattages. And then moving on to the next function, battery module. This is the fixed 6-cell EV module, and this is where we set up the thermal resistant network of the battery. We compute the HA, which computes the effective thermal conductance from the cell to the coolant plate. And then we build up the G matrix, which constructs like a matrix that defines the thermal coupling between the cells. And as such, essentially that is how much heat flows between the neighboring cells. And then we set up the cell ODE that defines the differential equations for the cell temperatures, which includes, again, the internal heat generation and the heat transfer to the coolant and the heat conduction between the cells. And then the coolant and cold plate node, it takes all of these inputs, and all of those inputs are explained here. And the goal of this function is to model the coolant temperature inside the cold plate. So it accounts for the heat entering from the battery cells, as we can see here, and what we calculated before, and the heat removed by the radiator, which is shown in this formula in this function, and the heat transported by the pump mass flow. So the coolant temperature dependent properties are used from the previous sections, and the output of this function is dTc over dt, and this time derivative of coolant temperature is what is passed on to the ODE solver later down here. The next section is for modeling the coolant pump, and this formula calculates the mass flow rate of the pumps and then looks at the power requirements of a centrifugal pump and also takes an integral of that power to calculate the total energy that is required to run the pump for a certain time period. Then moving on to the next section, the ambient radiator and ambient temperature function. This is a simple radiator heat loss function, and it computes the thermal power removed by the radiator based on the coolant to air temperature difference and the effective heat transfer between the two. And the next part is our longest function of this file, It runs the full thermal simulation of all of the parts that we just talked about before. It takes in all of these inputs and sets out the initial conditions and brings everything together into a thermal simulation. So it evaluates the user drive mode inputs and runs it through the pump model to determine the coolant mass flow rate and the pump power and then the total pump energy. This gives us how much coolant is moving at every moment, and after defining the initial conditions, it evaluates the pump flow over time, builds the cell's thermal network, and then combines the cell ODEs and coolant ODEs into a single system right here. And then combined ODE function represents the entire 6-cell module plus the coolant node as a seventh state system. Then SciPy uses the solve IVP to integrate the temperature over the desired time span right here. And then after that, we extract the results, the outputs that we want. We want the maximum cell temperature, the coolant temperature, the cell temperature uniformity, and the pump power and pump energy as well. And then the last block of code is for the main execution block. It just calls in all of those functions, and it runs the file directly, and it can also be called by the GUI, and this sets the drive mode, the ambient temperature, the coolant type, and the cell power, and so on and so forth. And the last part is the GUI basically wraps up all of the GUI functions and connects it to the Tinker GUI inputs and the simulation. And it maps the drop downs in the GUI to the strings that we have in the calculation file and runs the full simulation based on the user's inputs and returns the calculated value back to the GUI. And this allows the graphical interface, the GUI, to automatically update whenever the user changes the inputs, the drive load, the coolant type, and the ambient temperature, and so on and so forth.
Okay, hello class. So Kai just showed the thermo-prop v1 file, and now I'm going to briefly go through the app.py file, which really creates the GUI module. And here is the first section, which we define it as main, and we're first importing a lot of libraries. So Tkinter is a Python library where it has a lot of GUI elements that we are using, such as fonts, such as image TK, image ops, and we also have message box and different widgets that are really useful. And then we also included NumPy and Skippy, and then matplotlib, which helps us create graphs on the GUI module. And we also imported the coolprop library, which has thermodynamic properties of different coolants in case that's needed. And then for a lot of these, we included exceptions so that we're able to troubleshoot where an error is originating from. And so this file is very long, but basically it has 3 tabs. It has the overview, the diagram, and results tab. And each tab has a certain frame. But overall, we first had to create the original frame, which we are using the Notepad as the true window. And then we're using the widget frame to create frames within this notebook. And then we have another function called run simulation GUI, which takes in variables that the user inputs and stores it into these values, which will be used later on. And so this overview tab, we're creating a new frame for that overview tab, and we're calling it overview frame. So we included an image from this folder, so assets dash images dash backgrounds, and this is the image we chose. A lot of these like images or even new frames that we use, we create a function such that when the user changes the size of the window, the image or the frame gets resized as well. Like new frames inside the overview tab. So it's a frame within a frame within a frame. So these are going to be two frames that we're creating. We created the overview box frame, which it sits on the top and includes this this text, and then we created the key equations box, which includes this text, which is the key equations and assumptions. And now we're getting into the diagram tab, which has all the user input. So we first created some default text for certain types of labels we want to create. So we're using TTK, and then we're pulling that label widget, and we're creating it as select drive load profile. So this is for the drive load drop down. We have some for the coolant type, and then we also have one for the ambient temperature. So this is the results tab. We're first initializing string var objects that will hold the calculated results, and these results are retrieved from the thermo-prop v1 file. We set some, default fonts and sizes for certain types of labels we're creating. So there's output label font and output value font. And then we create a function to create layouts for the outputs into rows. So it's kind of like a matrix within the frame that we created. There's a definition called run simulation handler, where it takes the values from the user based on what their inputs are. And then this is a function we created to run the thermal simulation from the thermo.prop file, takes in all the inputs and calculates results from 0 to 1,800 seconds. And then it also calculates the maximum and average values for the temperature of the coolant and battery. And in this section, we included how the plots are going to look like. So there's going to be 3 plots, and we use subplots so that they can be distributed evenly. And this is just kind of, setting the X and Y plot labels and what we are plotting. So it's going to be temperature, it's going to be the pump power, etc.
Here we have our fully up and running GUI. Starting at the top left corner, we have the overview, input, and the results tab. And in the overview tab, we have the project objectives, where it states some of our background and motivations behind our model, and also some of the goals as well. And below that, we have the key equations and assumptions, stating some of the equations and assumptions that were made in the model. And on the right side, we have the schematics for our battery thermal management system. More information can be found in our document, but it states the flow diagram and the basic inputs and outputs of our system. Moving on to the second tab, we have our inputs. The user has a choice between the drive load and the coolant type, and the ambient temperature as well. And once the user inputs that information, the results and the calculations can be found in the results tab. In the results tab, you can see the outputs of our calculations, and you can see the maximum temperature of the cell, the average temperature, the coolant temperature, and the pump power as well. And as the drive load changes, you can see the pump power increases and decreases dramatically to cool off the coolant to a certain temperature range. And you can see as the coolant type changes, there are slight increases and decreases in the temperature. And you can see that the ambient temperature has great impact in where the coolant temperature settles as the time goes to infinity.